All right, this is the fourth FRQ for the 2019 BC exam. So we have a cylindrical barrel. So this is basically a cylinder, right? And that they gave you the volume of a cylinder is V equals pi r squared H. So it contains 2 feet, diameter of 2 feet. We don't want diameter, we want radius of 1 foot. The water drains out through a valve that's not shown. The rate of change of the height is measured this way. So the rate of change of the height is in terms of the height, where H is measured in feet and T is measured in seconds. Find the rate of change of the volume of water in the barrel with respect to time. So what I went ahead and did first is kind of write down all the information that I know. This is a related rates question because you're talking about the change of volume in relation to time, the change of height in relation to time. So you've got a lot of variables going on there and a lot of rates of change of those variables. So first I said, okay, if my diameter is 2 feet, then my radius is 1 foot. So that's important. The rate of change of the radius is 0, and I can tell because the radius is consistent throughout the whole picture. This picture doesn't change at all, so that's important. Then I knew that the height was 4. Because of part A, they said the height is 4 in part A. And then to figure out what dH dt was, I just had to do dH dt evaluated at h equals 4, which is -2/10 or -1/5. All right, and then it says you're finding the rate of change of the volume. So I said dV dt. Now I know that sometimes in problems, if we would try to get the entire problem in terms of one variable, and I think that feels a little bit complicated here. For me, that felt a little intimidating. So what I did is I just went ahead and used the product rule with this and left it in terms of R and H and just knew I have the radius, I have the rate of change of the radius, I have the height, I have the rate of change of the height. So I can plug all these numbers in and some of it's just going to zero out, which is totally fine. So pi r squared times H, I've got the first times the derivative of the second. The derivative of H is 1 times dH dt, plus the second times the derivative of the first. That's going to be 2 pi r times dr dt. And then I can go ahead and just plug everything in. And so pi 1 squared times -1/5 plus 4, 2 pi 1 times 0, so that's nothing, because that rate of change of the radius is nothing. And then I get that the rate of change of the volume is -1 pi 5th, and they want the units on that, so I know that it's a volume, so it's going to be cubed. And then I know that it's in relation to time, so I'm going to have something cubed per some sort of time. So they talk about feet, so I know that this is feet cubed. And then the time, the unit of time on the rate of change of the height was feet per second. And so this would be feet cubed per second. Or the other way you could have figured that out is to put all the units in your calculations, and then if you put all the units in your calculations, you would have been able to multiply the units out and get that same answer. All right. Part B says when you have that rate of change, or when the height is 3 feet water, is the rate of change of the height of the water with respect to time increasing or decreasing? So we have the rate of change of the height of the water to see, so that's your dH dt, to see if that's increasing or decreasing, we just need to take the derivative of that. So here's your implicit differentiation. So I have the second derivative is -1/20 h to the -1/2 times dH dt, so times the derivative of h, and then so that's -1/20, there's the square root of h right there. For dH dt, the square root of h would be on top. So these actually cancel, and I get that the second derivative is positive 1 over 200, and so since that is greater than 0, that means that it's increasing at h equals 3, and it's actually increasing always. All right, part C wants you to use separation of variables to find an expression for h in terms of t, and they give you 0, 5, so they're saying find the equation, you need to have the plus c in it, but you do need to solve for your c. So I'm going to say dh dt is negative 1/10 square root h. So I'll divide the root h over. And then, so there's my separation of variables. I'm going to integrate each side. So that's h to the negative 1/2. I'll just go ahead and write that. H to the negative 1/2. I'm going to add 1 to it, divide by that. So that's positive 1/2. So I've got 2h equals negative 1/10 t plus c. Oh, that was to the positive 1/2. Sorry, I missed that. Okay, so this is h to the positive 1/2. It was divided by 1/2, so it was really being multiplied by 2. And then I have the 0.05, and it doesn't really matter when I plug that in. I'll go ahead and, I'll just go ahead and divide by 2 real quick. So I have h to the 1/2, and then I've got negative 1/20 t plus c. A constant divided by 2 is still a constant, so that's why I just left it as c. And now I can go ahead and plug in 0.5. So I have 5 to the 1/2 equals negative 1/20 times 0 plus c. So 5 to the 1/2 is c, which means that the square root of 5 is c. Okay, so I'm going to go back to this point. And actually, if you want, you can go ahead and just call that square root h now. And then I'll square both sides. And leave it just like that.